Singularities in robotic arms. Today we're going to consider an example in which we have a planar 2 degrees of freedom robotic arm. It has two revolute joints represented with theta 1 and theta 2 dot here. In a previous lecture we already solved for the Cartesian velocities, or we also call them the linear velocities of the end effector x dot and y dot, as a function of the joint rates theta 1 dot and theta 2 dot. And today we're going to answer the question, under which conditions would there be a singularity for this robotic arm? So coming back to the same equation that relates the linear velocities of the end effector to the linear velocity of the end effector to the joint rates, where we have here the we call it the Cartesian part of the Jacobian matrix, which it's related to the linear velocities. It does not include the angular the part of the Jacobian matrix which relates to the angular velocities. But for simplicity, we're just going to call it the Jacobian matrix, even though it's only a sub-matrix of the complete Jacobian matrix. But here we're just going to call it the Jacobian matrix. So if you multiply both sides of this equation by the inverse of the Jacobian matrix, we can see here. So we have here the multiplication of the matrix by its inverse. So, and we already know that if you multiply a matrix by its inverse, this is going to give you the identity matrix, as we can see here. And multiplying by the identity matrix, it's similar to multiplying a number by 1, which gives you the same number, or in this case will give me the same column matrix. Now, what I'm going to do here is just rewrite the equation such as the joint rates are on the left side of the equation and the rest of the matrices are on the right side of the equation. So now what we have is the joint rates, or the angular velocities of the joints 1 and 2 as a function of the linear velocity of the end effector. And we mentioned before that this is a very useful equation, or a way of representing the kinematics of a robotic arm, because it's very useful in path planning, or in trajectory planning, because in this way, if you know the increments, the required increments in x and y, so you know delta x and delta y, in order to move along a certain path, you can, using this equation, compute the required delta theta and theta 1 and theta 2 in the same increment in time. So, and thus we can control the end effector to move along this path, because the changes in theta can be easily sent to the servo motor through the microcontroller. So, but however, before really using this equation, we need to find the inverse of the Jacobian. And the way to find the inverse, one of the ways to find the inverse, is to take the adjoint matrix of the Jacobian matrix here and divide by the determinant of the matrix itself. So the adjoint matrix is simply obtained for a 2 by 2 matrix. Is easy, really. It's you just need to. So this is the original matrix here. You need to interchange the diagonal elements. So L2 becomes here, and L1 S1 becomes here, as you can see. And for the f of diagonal elements, you just multiply them by -1, and everything you just divided by the determinant of the matrix, and the determinant is computed by multiplying L1 S2 by L2 minus the multiplication of these two elements. However, this is going to be 0, so simply the determinant is going to be L1 L2 sine 2, and sine 2, which is represents sine theta 2. So now we have this is the inverse, and now we can have the equation explicitly written. So we have the joint rates as a function of the linear velocities. Now we need to answer a couple of questions. The first question would be, when would the determinant of the Jacobian matrix become equal to 0? When would the determinant of the Jacobian matrix, and this is the determinant here, become equal to 0? It would become equal to 0 whenever sine theta 2 is equal to 0, because L1 and L2 are constants. These are the lengths of the robotic arm, L1, and this is L2. So it will only be equal to 0 whenever sine theta 2 is equal to 0. And sine theta 2 will be equal to 0 under two conditions. One at which theta 2 is equal to 0, or theta 2 is equal to 180. The case where theta 2 is equal to 0 corresponds to the case where the robotic arm is completely stretched out. In that case, the first link would be parallel to the second link, both of them extending along one line, as if we have lost 1 degree of freedom in this case. And for the other case is when theta 2 is equal to 180. This represents the case when link 2 is completely folded back on itself on link 1, and in this case it is as if we also have lost this joint, and the robotic arm now consists of only one link, which is has a link of L1, because L2 is completely folded back on it. So two cases, one for theta 2 is equal 0 and one for theta 2 equal 180. So we answered here the first question. The second question would be, what does it mathematically mean to have the determinant of the Jacobian matrix equal to 0? So mathematically, what does it mean that this is equal to 0? It means that there is this matrix, which is in this case the Jacobian matrix, is a singular matrix, and it means it doesn't have an inverse. So what does it physically mean to have the determinant of the Jacobian matrix equal to 0? Or in other words, what does it physically mean for the Jacobian matrix to be a singular matrix and thus not to have an inverse? It simply means that there isn't a solution for this equation here, which means that you cannot find values for theta 1 dot and theta 2 dot to acquire a certain x dot and y dot. Because as you see, if sine theta 2 becomes 0, it means the whole term here will go to infinity. It means that you will need very large values going up to infinity for theta 1 dot and theta 2 dot in order to achieve any certain value of the linear velocities of the end effector. So for any value, you can choose any value here of x dot and y dot, and you will see that it's really impossible to reach that. Under which conditions? Under the conditions where theta 2 is equal to 0 or theta 2 equal to 180. So under these conditions, you cannot really obtain or acquire those linear velocities, because it would require very high values of theta 1 dot and theta 2 dot, values that would need to go up to infinity, and which is not really attainable in reality. So in this slide, we have a summary of the answers that we got for the three previous questions. We have two conditions under which we will have singularity points. The first one having theta 2 equal to 0, which means that the robotic arm is completely stretched out. The other condition occurs when theta 2 is equal to 180, and this represents the case where the robotic arm is folded back on itself, And this would happen when the Jacobian is a singular matrix for which the determinant is equal to 0, and thus the Jacobian matrix has no inverse. And we said that physically it means that there would be no values of theta 1, no reasonable values for theta 1, theta 2 dot to attain any given x dot and y dot using this equation. So what does it really mean? I mean, if we just want to look for one statement, it doesn't mean that we will not be able to control the robotic arm. It simply means that we cannot use this equation to control the robotic arm when theta has values of around 0 and 180. Because you can still send a command to the servo motors and change theta 1 and still change theta 2, but the only thing is that you cannot depend on this equation to control it under these two conditions. That's it for today. This is another example of a planar 2 degrees of freedom robotic arm. This time it's a Revolute-prismatic robotic arm. We have theta 1 here and we have d2, both of which are variable. And in a previous lecture, we were able to obtain the relationship between x dot, y dot of the end effector as a function of these join rates, theta 1 dot and d2 dot. And this we call the Jacobian matrix, or simply the linear velocity portion of the Jacobian matrix. And we are now asked to find under which conditions would there be a singularity for this manipulator. So for looking for the singularities, we're gonna look at the determinant of the Jacobian, set this determinant equal to 0, and see under which conditions there will be no inverse. And so this is the determinant. If we take this element times this one here, minus this element times this one. And you will see that we'll have a cosine squared, a sine squared, and in both cases they are multiplied by, both of them are multiplied by d2 plus L2. So we can write this equation as d2 plus L2 times the summation of cosine squared plus sine squared, and we set this equal to 0. Here we have a trigonometric identity that will give me a value of 1, which the result will be that the Jacobian, or the determinant of the Jacobian, would be equal to 0 whenever d2 is equal to minus L2. And d2 would be equal to minus L2 whenever the end effector reaches point 0. And it's not necessarily that d2 is allowed to go to this value. However, this is what we get from just looking at the equations, and it makes sense. So once the end effector is at at the origin of frame 0, you will have a singularity. That concludes our lecture for today. Thank you.